So the Square Kilometre Array is an international project of about 13 countries and over 100 institutions to build the world's largest radio telescope. This radio telescope is based in two parts, a part of it in Western Australia and a part of it in South Africa. Countries are producing competing technologies in order to produce the best technology which can be the most sensitive to receiving these radio waves from extragalactic sources and stars in our galaxy. Here at the Institute of Space Sciences and Astronomy at the University of Malta, we are carrying out research in how the universe started, how it evolves, and a lot of the global celestial bodies that we see in our sky. What we are building here as part of our funding from MCST and the Malta Communications Authority, we have built a radio telescope. A radio telescope works a little bit different from that of an optical telescope, in the sense that an optical telescope uses a lens to focus the light coming from the stars onto our retina, whereas a radio telescope uses a parabolic dish, like we can see in the background today, in order to focus the radio rays coming from radio sources like galaxies and stars onto the focus of the dish. Traditional radio telescopes use mechanical structures, for example, the shape of a dish, in order to focus the radio waves into the focus of the dish. What the new telescope we have designed in Malta, and is now the new future generation of radio telescopes, is that we receive all the signals on a flat bed of radio telescopes and then combine to form the focusing in software. So everything is done in a digital software kind of way. This gives us a much more flexible way of creating the surface of the dish, and also for correcting in software the aberrations that the dish surface might have.
Now this is our antenna. Basically, this is our proposed antenna. It's silver printed patches, and it resembles cross-polarization dipole. So we have, this is one dipole and this is the second dipole. So it is dual polarization in order to increase the field of view. So we can scan the sky from -45 degree to +45 degree. And it will give us large possibility of scanning the sky. In order to test the sensitivity antenna, we have developed a test run procedure that involves flying a drone. The drone is installed with a transmitter, such as transmits signals being received by the antenna under test, which is on the ground. And we predefine the path of the drone, so it can be a flight by autopilot over a distance of 100 meters in order to resemble a far field flying source. Our research project designed and developed antennas that are novel, and they are just not only capable of dropping the cost of large element, they are also planar structure and can be printed out easily, such as the newspaper. The next step is from scaling up the antenna, because we started with a small structure, about 250 elements, that as the first testing of our array design. And once the results were promising, we went for a large scale, which is 5,000 elements, which resembles an area of 100 meters square. There are a lot of measurements which has to be conducted in order to verify that if the antenna we propose meets the square kilometer array. One of them is to put forward a real testing of receiving cosmos radiation pattern and post-process the data and visualize if we can get image from the sky.
This research was funded through the Technology Development Program of the MCST, because MCST recognized the fact that if we build a prototype here at the University of Malta, this prototype can then be used and tested in Western Australia in order to be able to understand how much better this technology that is produced in Malta is than the competing technology. The Malta Communications Authority also contributed to funding of this project, because they recognize that these antennas can also be used in things like communications, for example in mobile phone masts, and for example for maritime surveillance.